Hello everyone, welcome to tutorial number 8 for EC457A. The topic of today's tutorial will be mixed strategies as well as continuous strategies. So let's get started. So for mixed strategies, we will go through two examples. So the first example is a head-tail game. So this is player 1 and this is player 2. So as you can see in this game, there is no pure strategy, pure Nash equilibrium in this game. So there is no Nash equilibrium. So if we play this game, we should be on predictable. All right. Therefore, we must randomize or mix between strategies. All right. The first approach is actually first order condition. So we say that for player 1, H happens with a probability of theta, and for tail, it happens with a probability of 1 minus theta. And this is also the case for player 2, H happens with the probability of alpha, for example, and T happens with a probability of 1 minus alpha. So the whole probability for player 1, pi p1, will be, all right, so we have theta multiplied by 1 alpha plus negative 1 minus alpha. Now for tail, 1 minus theta, negative 1 alpha plus 1 minus alpha. All right. So what we get here is for alpha theta minus 2 theta minus 2 alpha plus 1. And for the next one, for player 2, okay, so for player 2, what we have here is alpha, -1 and 1. So -1 theta, 1 multiplied by 1 minus theta. And then for the second part, or the second action, tail, 1 minus alpha multiplied by 1 theta plus -1, 1 minus theta. So alpha multiplied by -1 theta plus 1 minus theta. And for tail, we will have 1 minus alpha and 1 theta plus -1, 1 minus theta. And this will result in -4 alpha theta plus 2 theta plus 2 alpha minus 1. Okay. Because we will be needing these terms further on, let me write them down. This one will be 2 alpha minus 1. This one will be -2 alpha plus 1. This term is -2 theta plus 1, and obviously this term will be 2 theta minus 1. Okay. So what we need here is to take the derivative of the probability of player 1 with respect to theta. So we will have partial derivative of pi p1 over with respect to theta, which is equal to 4 alpha minus 2, set it equal to 0, and that will give you alpha equals 0.5. And for next one, partial derivative of the probability of P2, player number 2, with respect to alpha, would result in -4 theta plus 2 equals 0, and theta will be 0.5 as well. Also, we need to check to see if these points are like a maximum of the curve, like a maximum value. In order to check that, we need to see if they are less than or equal to 0. So the second partial derivative of P1 with respect to theta is equal to 0, which is greater than or equal to 0. It's correct. The next one, P2 with respect to alpha equals 0, greater than or equal to 0, and less than or equal to 0, and it's also true. So this is the probability that probabilities we found for this example. So for example, the player 1 plays either H or T with probability of 0.5, and this is also the case for player number 2. Let's move on to the second approach, payoff equating method. Now let's solve this one with payoff equating method. So what we need to do here is to equate these two terms together, and these two terms together. So for player 1, we will have 2 alpha minus 1 equals negative 2 alpha plus 1, which results in 0.5, same value. And for the second player, negative 2 theta plus 1 equals 2 theta minus 1. Yes. Which is 0.5 as well. All right, so makes strategies. Let's say that example 1. We have another example. Makes strategies. Example 2. Okay, so this is a 3x3 matrix. Three, 2, 2, 1, 1, 3, 4, 2, 2, 2, 3, 1, 5, 2, 1, and 1, 3. Okay. This is U, M, D, action L, M, R, and player 2 and player 1. All right. So, because this is a 3x3 matrix, we need to get rid of as many strategies as we can, because this way it is somehow impossible to use mixed strategies to solve for this example. So we need to get rid of as many strategies as we can. All right. So let's see. For player 1, we can see that M actually is completely dominated by it's also dominated by D, but it's completely dominated by U as well. So 3, 2, 2, 1, 1, 0. So we can actually get rid of this one. And then for the other player, we can see that M is dominated by L. So this is this is 2, this is 1, 1, 5. So in this case, M has a greater value, but 3, 2. So we have two values, 3, 2, and 2 greater than 1. So we can say that L dominates M, or M is dominated by L. Therefore, we can get rid of M as well. And we will end up with 3, 2, 1, 3, 3, and 2, 2. Okay, so for player 1, M is completely dominated by U. And for player number 2, M is dominated by L. 2 more over here. Okay. Now we can move on to the strategies, the approaches that we can take. So the first one is first order condition. I need to add a new page here. Current template. Okay. So for the total probabilities of player 1, first of all, we have theta over here, alpha, 1 minus alpha, and 1 minus theta. The total probability for player 1 equals theta three alpha plus 1 minus alpha plus 1 minus theta, and 1 alpha plus 2 1 minus alpha. And this will be 3 alpha theta minus alpha minus theta plus 2. And for the other player, that would be alpha 2 theta plus 3 1 minus theta plus, oops, sorry, I made a mistake over here. Minus theta. 1 minus alpha. And, okay, 3 theta and 2 1 minus theta, which is negative 2 alpha theta plus alpha minus theta. Sorry, plus theta plus 2, I believe. And okay. And because we need these values further on, let's say, okay, so this one is 2 alpha plus 1. This one is negative alpha plus 1 plus 2, sorry. This one negative theta plus 3. And this one theta plus 2. Okay. All right, now, so the first approach we said that is FOC, first order condition. We need to find the derivative of the partial derivative of the total probability of the first player with respect to theta, which would be 3 alpha minus 1 equal to 0. And alpha is 1 over 3. And now let's check if this is a maximum for this function with a second derivative. Which is 0. Yes. Let's do it for the other one, which is partial derivative of player 2 with respect to alpha, and then the second derivative this one is negative 2 theta plus 1 equals 0, and theta is 1 over 2. This one is also 0. So this is the maximum value. Okay, so the first player plays U and D with both of them with a probability of 0.5, but this one is the first player, yes. And the second player plays L with a probability of 1 over 3 and R with a probability of 2 over 3. Now let's solve this problem with the other approach. Payoff equating method. And I need to add another one. All right. So in this case, we need to equate these two terms with each other, this term and this term, and these two with each other as well. So for player 1, we can say that 2 alpha plus 1 equals negative alpha plus 2. This gives us alpha 1 over 3. Same thing. And for P2, negative theta plus 3 equals theta plus 2. We will end up with theta equals 1 over 2. And yes, that's it. All right, so that was for the mixed strategies, 2 examples. And now let's move on to continuous strategies. All right, so in this example, we are going to go through corner competition, as well as Stackelberg. Competition. So this is a example similar to what you have in your lecture notes slides. We have a profit per quantity function. That is P of Q. In this case, it's equal to 9 minus Q1 minus Q2. So we have 2 companies competing with each other. Then we have the total output. Which is Q equals Q1 plus Q2. And then we have the marginal cost per marketing. So the marginal cost okay, so here the marginal cost is a function. It's C of Q, and it's equal to 2Q. You can consider that as like C value is equal to 2. Like the notation you have in the slides in your lecture. All right. Let's get started and solve this with the Coronel competition method, actually. So in this case, let me write down the payoffs as well, because for Stackelberg and Coronel, they're the same. So payoffs for the first company, the payoff is like PQ Q1 minus CQ1, which is 9 minus Q1 minus Q2 Q1 minus 2 Q1. Okay, and for the second company, that would be PQ Q2 minus CQ2, which is 9 minus Q1 minus Q2 Q2 minus 2 Q2. Okay, so these are the payoffs. Let's also add another one. Okay. So the first method, kernel. In this case, we need to find the reaction functions. So R1 is equal to partial derivative of the payoff of the first company with respect to Q1, the quantity of the first company. It will result in 7 minus 2 Q1 minus Q2 equal to 0. And for the second company, that would be 7 minus Q1 minus 2 Q2. And we need to find the Corno-Nash equilibrium. That would be that actually comes from equating the R1 and R2. Which result in Q1 equals to Q2. Okay. Now that we have another equation, we can use this one, substitute Q for Q2. So that would be R1 equals 7 minus 2Q1 minus Q1 equals 0. And Q1 is 7 over 3, which is actually Q2 as well. Sorry, which is equal to Q2. All right, so the total market output in this case is Q, which is Q1 plus Q2, which is 14 over 3. All right. Now let's go and solve this problem with Stackelberg competition. So the payoffs are the same. We only need to find the leader and the follower. Stackelberg. Okay, let us assume that player 2 moves first. So in the lecture notes, you assume that player 1 moves first. Now, let's do the opposite. Let's assume here that the player 2 moves first. In this case, player 2 is the Stackelberg leader. So player 2 is the Stackelberg leader, while player 1 Stackelberg follower. All right. So in this case, player 2, because is the leader, predicts the reaction function of player 1. Therefore, player 2 predicts the reaction function of player 1. So reaction function of player 1. What is the reaction function of player 1? That would be R1, and is a partial derivative of the payoff for the first company or the first player with respect to Q1 or its quantity, which is equal to 7 minus 2 Q1 minus Q2 equals 0. So player 2 predicts the reaction function of player 1. This gives us for player 1 7 minus Q2 over 2. What we need to do is to substitute this into the payoff of the second player, second company. So here we have 7 minus Q1. We know that Q1 is this value, and minus 2 Q2. Sorry, this is the reaction function. No, this one here, over here. We need to substitute what we found for Q1 here in the payoff. So in this case, there we 9 plus Q2 minus 7 over 2 minus Q2 minus 2 Q2. And now, taking the derivative, or finding the reaction function, that would be 7 minus 7 over 2 minus Q2 equals 0. Therefore, Q2 is equal to 7 over 2 And because of this, we can say that Q1 equals 7/4 with substitution. All right. So these are the values that we found with Stekelberg. Yes. Now let's compare them. That will be a good practice. All right, so note that Q, the total output is Q1 plus Q2, and here it's equal to 7/4 plus 7/2 equals 21/4. Now, a good point here okay. A good point here is to note that if player 1 moved first, let me write it like this. So P1 follower, P2 leader. In this case, Q1 is 7/2, Q2 7/4, and Q2 7/2. Now, if player 1 was the leader and player 2 was the follower, Q1 would be 7/2 and Q2 would be 7/4, and the total is the same. Okay, same total. Now let's compare them. I've written down a comparison between these two methods here, and let's go through it. Let's divide the page to two parts. First one is kernel, and the second one is Tekelberg. So for the first method, we had Q1 equals Q2. Both of them were 7/3, which is 2.37. And here we had Q1 equals 7/4, which is 1.75. Q2 was 7/2, which is 3.5. Now the total, Q1 plus Q2, it was 14/3, approximately 4.67. And for the other method, Q1, Q2 equals 21/4, which is 5.25. And PQ here for kernel was 4.33. So the profit in here was 3.75. And the consumers would prefer the Stekelberg method and quantity and profit and cost over the cardinal. Why? Because most total output we have over here with lowest price. Therefore, this method is the consumer's preference. All right. Now let's move on to the last example. Continuous strategies, Bertrand. Two firms setting price. Simultaneously, like at the same time. All right. The terms that we have the first quantity. So the difference is here that we have the quantities as a function of prices. So we have two companies, the quantity for the first company and the quantity for the second company. Both are functions based on the price of the first company and the price offered by the second company. This is a very simple example, nothing complicated. And the marginal cost, also let's assume the marginal cost is 0. For both. All right, so the first step is to write the payoffs. For the first company, that will be Q1 multiplied by P1 minus C. For the second company, that will be Q2 P2 minus C. And we also mentioned that the marginal costs are 0. So we have 72 Q1. Okay, so we will have 72 Q1. Sorry, why Q1? P1, 72 P1 minus 3 P1 squared plus 2 P1 P2, and for the other one that would be 72 P2 plus 2 P1 P2 minus 3 P2 squared. Okay. Now what we need to do is to use the first order optimality condition. So that would be taking the derivative of the payoffs with respect to the probabilities in this case, not the quantities, but the probabilities. But the prices, P1 and P2. Take a derivative of payoffs with respect to probabilities. That would somehow give us the reaction functions. So I need a new page. Okay. So for the first company, R1 equals partial derivative pi 1 with respect to P1. That'll be 72 minus 6 P1 plus 2 P2 equals 0. R2 72 plus 2 P1 minus 6 P2 equals 0. R1 equals R2. In this case, negative 6P1 plus 2P2 equals 2P1 minus 6P2, and you can see that P1 is equal to P2. Okay, now we can substitute this equation in one of them, so there's no difference. We can use this one, bring it over here, and say that 72 minus 6P1 plus 2, not P2, but P1 equals 0. P1 equals 18, which is also P2. So we found a price for the first and the second company. And now if you substitute P1 and P2 into the into these two equations over here, this and this, we can see that Q1 equals Q2. Both of them are 54, so this is the quantity, and the total output will be Q1 plus Q2, 108. So total output with this price. And that's it for tutorial number 8. These are the references and PDF files that I use the examples within them. You can check them out. Until next time.